In 2.5, we look at some applications of matrices. And the first application we're going to look at involves stochastic matrices. And in order for a matrix to be stochastic, each column has to add to 1. Basically, what these represent will be probabilities. And they're going to be used to calculate some probabilities, to see how populations change over time given certain details and certain likelihoods of things occurring. So we'll look at an example. And the first example we're going to look at is number 8 out of the book. And number 8 describes a medical researcher studying the spread of a virus in a population of 1,000 laboratory mice. During any week, there's an 80% probability that an infected mouse will overcome a virus. And during that same week, 10% of, non-infected will become infected. So to begin with, what we're going to do is we're going to set up a probability matrix. We have two possibilities. Either something is infected or it's not infected. And our columns are going to represent the position that we first find the rats in, and the rows are going to represent their transition. So let's let the first column represent infected rats, the second column non-infected rats, the first row infected, the second row non-infected. So let's take this and let's see what that tells us. So 80% of rats that are infected, so they start out infected, they overcome it, which means they become not infected. So those that were infected become not infected. That's 80%, 4.8. Which means that since this is stochastic, remember this adds up to 100% or 1. That means 20% that were infected stay infected. Now, out of the ones that started out non-infected, 10% become infected. So non-infected that become infected, that's 10%, which means 90% of the non-infected stay non-infected. So this is a stochastic matrix that we can use to determine the transition of infected, non-infected rats over a certain period of time. So what we'll do is we'll have a column vector that we'll use as our input. So if we know the population's parameters at a certain time, we could find out, well, from week to week, what should we expect? So the end of this says 100 mice are currently infected with a virus. And remember, we started out with 1,000. So we're going to use the same rows, infected and non-infected. So if 100 are infected, and we have 1,000 overall, that means 900 are not infected. So we're going to take these two matrices together, and that's going to let us know how many of each case do we have, how many infected, how many non-infected after this first week. So if we multiply these two together, this row times this column, 0.2 times 100, that's 20. 0.1 times 900, that's 90. 0.8 times 100, that's 80. 0.9 times 900, 810. So what's that? 110, 890. Notice these still add up to 100. So we had 110 now that are infected, 890 now that are not infected. If we wanted to say, well, this is after 1 week, what about after 2 weeks? Then we would take our stochastic transition matrix and we would multiply our new result by that. So 0.2 times 110, 22. 0.1 times 890 is 89. 0.8 times 110, 88. 0.9 times 890, 801. So 111 infected, 889 that are not infected. Notice there we didn't get much change. After a while, we have relatively no change from 1 week to the next week. And once we reach that point, this is called a steady state. So our population is going to, in general, maintain these parameters. There will be roughly 111 infected, 889 that are not infected as we progress throughout the following weeks. So that's one application of matrices. Another application of matrices we're going to look at is decoding and encoding messages. The next thing we'll look at will be decoding and encoding messages as an application of matrices. And to begin with, let's look at this little picture here. And I guess we can copy that over. So let's let each letter be represented by the corresponding number. So first of all, if we need a blank or a gap between two words, that'll be represented by the number 0. If we have a letter A, that'll be 1, letter B, 2, and so forth. So if I wrote, I am me, then that would be 9, followed by space, A, M, space, M, E. 1, I, space, A, M, space, M, E. So those will be the numbers represented by that. But of course, if we just use that correspondence, that would be easy to break that code. If you're sending a message that you needed to be encrypted so that no one would know what you're saying except somebody else that has your code breaker, and they're the only ones that need to know what you're saying, that would be easy to break. So what we can do is we can use an encoding matrix. An example of an encoding matrix would be 1, -2, 2, -1, 1, 3, 1, -1, -4. And if we want to encode, let's say, this message, or we'll do the first part of it at least, then what we'll do is we'll multiply it by this encoding matrix. Now notice this has 3 rows, 3 columns. So we need to have 3 columns here. So generally what you do is you break your message up into individual rows. So let's just do 1 row here. So if we have 1 row, 3 columns, that means we have 3 spaces. So the first 3, those will be in this first matrix. We'll multiply that out, and then we'll use the same encoding matrix. And then we'll multiply the next 3 characters by the same encoding matrix. So the next 3 characters are 13, 0, 13. So that'll encrypt or code the next 3 characters. If the last 2 characters should be blanks, why the last 2 characters? Because for our dimensions to match up, we do have to have 3 columns. Since we have 3 rows here, we only have 1 character left, so everything else would be blank. So the last one would be 500. So if we want to use this and encode, let's multiply this out. So row times column, so 9, 0, 1, that'll give us 10. This row times this column, so -18, 0, -1, so -18, -1, -19. 9 times 2 is 18, 0, 4. 18 and -4 is 14. 18, 0, -4. 18 minus 4. Here, 13 times 1, that's 13, 0, 13, so 26. Minus 26, 0, minus 13, so minus 39. 26, 0, minus 52, so 26 minus 52 minus 26. So we've taken these, we've encoded them, and we've got those. This one, and we got that. So whoever we send the message to, this will be our hidden message. So once we send that, somebody is going to need to decode that, and the way you decode that is you use the inverse of the encoding matrix. So if our encoding matrix was this, then the decoding matrix would be the inverse of that. And I'll just give that to you real quickly. Make sure that I wrote the first one down correctly. Right. So the inverse of that, -1, -10, -8, -1, -6, -5, 0, -1, -1. So we'll decode the same way we encoded. So if our coded message is 10, -19, 14, 10, negative 19, positive 14. Then we'll multiply that by our decoding matrix. And we should get the row matrix, the row vector out that we begin with. So 10 times negative 1 is negative 10. 19, 0, so 9. Did we start with a 9 there? Yes. Row times column. That's negative 100. 19 times 6. That's 19 times 6. 114. 14 times minus 1, negative 14. That's negative 114. Positive 114 is 0. That was our next value. So that's correct. And then row times column, negative 80. Positive 95. Minus 14. So this is minus 94 plus 95, so 1. 901, that was our first encoded, or our first uncoded script that we were decoding. We re-encoded it, we got back to what we started with. So without having this quote-unquote enigma, without having this matrix that will code and uncode, then it would be very difficult to figure out what the hidden message was if we were just given these. So that's decoding and encoding using matrices. Let's look at one more application system where matrices are useful. And one example would be in managing natural resources or production of goods. Let's suppose we have a 2x2 matrix that represents how much input of certain resources you need and then the corresponding output of resources. So let's suppose we're wanting to manufacture electricity and coal. So let's say to make 1 unit of electricity, let's suppose it takes 2/10 of a unit of coal, or actually let's increase that. Let's say it takes half of a unit of coal, and you also have to have something running those machines. So let's say it takes 2/10 of a unit of electricity to run the machines that are taking the coal and breaking it down and then turning it into heat, which they're using to turn turbines to produce electricity. So it takes both coal and electricity to produce electricity. And let's say to produce 1 unit of coal, it's going to take, let's see how I set this up earlier. We're going to use 5 units of coal, and then we're going to take some electricity to break that down. So in the manufacturing of 1 unit of coal, or as we end for 1 unit of coal, on 1 unit of coal, we're going to end up with a half unit of coal used and 0.3 of electricity used. So if we input, let's put electricity here, coal here, electricity here, coal here. So if we're making electricity, that takes 0.2 units of electricity, 0.5 units of coal. And now I'm just making some numbers up, so these may or may not make a whole lot of sense as far as actual production. But just follow where we're going with this, and then the numbers you're given might make more sense. If we're dealing with outputting coal, then we have to input coal and electricity. So let's see. Let's suppose that we start with 100 and 200 as our requirements for coal, or for electricity and coal. So let's suppose we were to multiply these two together. So we have a 2 by 2 times a 2 by 1. So we're going to output a 2 by 1. Row times column, 0.2 times 100, 20. 0.3 times 200, that's 60. So that's how much electricity is needed to produce this amount of electricity. For the actual production of electricity, if we need to make that, then it takes 20% of a unit of electricity to produce that electricity. But we also have to have coal. Coal is going to be used to make electricity, so 0.3 times the amount of coal, 60. How much coal do we need? 0.5 times 100, 50. 0.5 times 200, that's 100. So 80 units of electricity, 150 units of coal. So again, my numbers don't actually work out, because if we're outputting 200 units of coal, why are we inputting 150? But it is good if we're outputting 100 units of electricity to only take 80 as our input. So this is how much electricity and coal is required. This is how much we put in. So to get these values, this is called our demand or distribution matrix. Let's call this D. This is our output matrix, X. So to get this requirement, we took D times X. So this times this, so D row 1, column 1 times X1 plus D row 1, column 2 times X2, and that gave us our new amount of electricity. That's how much electricity we need to output in order to generate what's demanded of us. So then we take the next one, row 2, column 1 times x1, row 2, column 2 times x2, and that'll give us our new x sub 2. So notice there are no outside factors in here. We're just figuring out how much electricity is needed to produce electricity and to produce coal, how much coal is needed to produce electricity and to produce coal. But in and of themselves, we need the electricity is needed by the outside world, coal is needed by the outside world. So if electricity and coal were only used to make each other, and that was the only use for them, then that would be a closed system. And this is how you would figure that. Take this times this, and that would give you your requirements, how much you need. So this is basically what the demand is, your internal demand multiplied, and that gives you how much is needed. But we also have external demands. So if we came in and added another column, how much electricity is needed, how much coal is needed, those would be from the external world. So this would be an open system. So let's take the first part of that, group that together. Let's call the matrix formed by those E, that's the external demand. So actually, let's go back. So this is electricity. How much coal the outside world needs. So when we multiply our need matrix, our original x1, x2, by our demand matrix, that gives us how much demand the coal and electricity industry need internally. And then we add how much electricity is demanded by the outside world, and that'll give us how much total electricity is needed. We do the same thing for coal, multiply the amount of coal, the requirements for electricity and coal to make coal, plus how much coal the outside world needs, and that tells us how much total coal is needed. So this is from taking your internal or your initial amount times your demand matrix. So if we want to look at this as a system, we have one system of equations here, or one equation here, one equation here. As a system, let's call the external demand E, where E is E times C. So if you take how much is required by the industries plus how much the external world needs, that gives you your total amount needed. So if we want to find out, hold on just a sec. Okay, again, so just for a little clarification, E, that's the external demand, and that's generally what we're going to be given. The market needs so many units of electricity to run all the houses, businesses, yada, yada, yada in the network. It needs so many units of coal to make the iron, to make the charcoal, make the different coal products in the production system. So these are what the external demands are. So how much internal coal and electricity is going to be used to actually get that output. So, of course, if we need to produce something, we said it takes coal to make coal, it takes electricity to make coal, it takes electricity to make electricity, coal to make electricity, and that doesn't even take into effect how much output we need for the rest of the world. So if we know what the output for everyone else is, this equation will help us find that. So let's solve this for E. Let's subtract dx from both sides. So the external demand equals x minus dx. So the question that we're eventually looking for is how much input do we need of each item of coal and of electricity so that we reach our external demand. So E, notice both of these terms have an x in them. Now, if we want to factor this out, we need to consider, okay, our understood coefficient there, we could call the identity matrix. The identity matrix times any matrix is that matrix. So if both of these have an x, notice the x is on the right side. We can factor x out on the right, and we're left with I minus D. Now, if D is this matrix, let's see, 0.2, 0.3, 0.5, 0.5, D, then I minus D is the corresponding identity matrix minus the demand matrix. So 1 minus 0.2, 0 minus 0.3, 0 minus 0.5, 1 minus 0.5. So that's I minus D. So if we need 1,000 units of electricity, 1,000 units of coal to be produced for the outside world, then E equals 0.8, negative 0.3, negative 0.5, 0.5 times x. Notice this is just a system of equations, so we can set this up as an augmented matrix, or we could use the inverse of this times that and solve for x. And that would tell us how much input we need of coal and electricity both to meet not only the internal demands of producing coal and electricity, but the external demands to feed the production system. So I know that was a little messy going through that, but we'll cover some of those in class if need be.